Now, it also wants you to investigate elements that possess physical properties of allotropy or allotropy, I like to call it allotropy, and electropy, probably the better way of saying it. Sometimes I put H in there. And then investigate the different chemical structures of atoms. So, allotropy, I can never say it properly. Allotropy refers to when an element appears in different forms due to the differences in bonding between each form. So graphite and diamond are literally made up of carbon. They are both made up of just carbon. Graphite and diamond look very, very different. So, oh, sorry, this got a bit squished up. I do apologize for that. I should have fixed that. But nonetheless, you'll get the point. Diamond and graphite are both made up of carbon. They're both networks of carbon. So carbon's a really cool molecule. However, diamond is a complex network, whereas graphite is distributed sheets. As you can see back here, this is like a really complex network where everything is sort of spaced out in weird ways. Graphite is just sheets. They're just sheets. Now, diamonds, because of this complex network, are one of the hardest structures we know to man. That's why diamonds were initially so expensive. Not only were they pretty, they were so hard. So hard, we could barely work with them, and we went, you know what? This is cool. Made them expensive, and now they're really expensive. Graphite, on the other hand, is still strong, but it's brittle. So if I smash a piece of graphite, it'll explode. Whereas if I smash a diamond, it's probably not going to do anything. Nothing's going to happen. So as you can see here, graphite has many layers where the carbons connect to three others. It consists of easily or even, I think I can say evenly distributed sheets. I don't think it's going to say easily. I think it's going to say evenly. Essentially, the soft sheets move apart as you hit them, and essentially they are brittle, so they break. Now, if you think about it, it's a really good way. Graphite is used in pencils, so you'll find those in pencils, whereas diamonds obviously are in jewelry. Now, ionic networks are referred to as lattices, and that consists of grid-altering positive and negative ions. So these are covalent bonds, remember? So carbon-carbon is covalent. Now, what if I had solid table salt? Table salt is a solid. So that is what we refer to as an ionic lattice, because table salt is made up of sodium and chlorine. It's held together by ionic bonds. What's really important is they have to alternate. They have to have one positive, then one negative, then a negative, then a positive, then a negative, then a positive. Like, they've got to be alternated. Think about it like balls in like a tub, and you've got to have them all alternated perfectly. What that also means is that if I hit that again, if I hit that ionic solid, if I hit a big thing of salt, I will push different layers against each other, and I'll push a positive, like let's just say I had a positive, and then a positive here, and I had negatives here, and I push this layer up, and now there's positives next to each other. They don't like each other. What do? Explode apart. So they are also really brittle. So because of this, we find that ionic substances have really high melting points and boiling points because they're really strong, but they're also really brittle. So if you hit it really hard, it'll just shatter. And that's really not a good thing. They only conduct electricity in a liquid state because they don't have the ability for a charged particle to move throughout when they're in the lattice. If you melt them down and make them into a liquid, well, all the particles are moving, so you can conduct electricity. So this is what I was trying to describe, that sort of image there. Now, covalent networks, as we've already sort of mentioned, we just mentioned the sort of diamond, and we mentioned the graphite. Now, covalent networks are usually they're always made up of nonmetals, but they are usually made with continuous covalent bonding, and they sort of go off into different directions. They usually, again, have high melting and high boiling points, and again, they do not conduct electricity as there's no ions, and the electrons are in a covalent bond, and hence there is no free roaming electrons to conduct electricity. There's no charged particles within covalent networks to be able to move an electron along. So remember, covalents are non-metals. So the only thing that can conduct electricity as a solid is a metal, just a pure metal. A pure metal is the only thing that can conduct electricity as a solid. It's a rule you should know. It's a rule you should stick by. If it's not a pure metal, it's like a singular pure metal, that is a solid, it cannot conduct electricity. Liquids are a bit different because most liquids can, but it varies. Covalent liquids usually cannot. The molecular formula of covalent networks also represents the ratio of atoms, etc. And we'll learn a lot more about covalent networks, particularly in organic chemistry. So covalent molecular compounds are composed of nonmetals that are held together by weak covalent bonding. Physical properties, they're not very hard. They're usually pretty malleable. This is because the covalent bonds have sheets of lattices like grids, which make it easy for these sheets to slide over each other. The only difference is sort of graphite, which is a little bit more break apart, a little bit more brittle, although it does sort of move okay. It's not as brittle as an ionic substance. An ionic substance is super brittle. They do not conduct electricity because they are all neutral. If an aqueous solution is created, they do not dissociate into ions, so again, they cannot conduct electricity ever. So what we're trying to say here is that HCl here is sort of an example here. It can conduct electricity. Sorry, I just got that mixed up. So in an aqueous solution, they do dissociate into ions, so they can conduct electricity. So what I mean by that is, sorry, I got those mixed up again. Essentially what happens is when you put a covalent molecular substance into a liquid form, so you melt it down, you end up with the ions again because there's so much energy there that it breaks those covalent bonds. They're not that strong. So when you break those covalent bonds, your H positive and your Cl minus, if you had HCl, then become ions again, and they're moving through that liquid, and because they're charged, they then conduct electricity. Sorry, I got those completely mixed up. You do conduct electricity as a covalent molecular substance as a liquid. As you can see here are some examples of it, ice, so forth. Now, metallic structures, these are very different because they do move electrons. They do have the ability to move electrons when they are a solid, and therefore the ability to move electrons means they can move a charge. And when they can move in a charge, what does that mean? When they can move a charge, they are able to conduct electricity. So they're really, really interesting in that point. So in that point of view, we really like metals because metals conduct electricity. We put them in wires. We sort of ductile them into wires, and we utilize them in a lot of our structures and so forth. So essentially what we refer to this as, and this is a really key wording that you need to know throughout this year and you need to know next year, is that metallic structures consist of a sea of delocalized electrons within a lattice of metal cations. This is the metallic bonding model, and it's something that you'll see, and I don't know why there's no images of it here, and I really want to grab up an image. So what I'm going to do very quickly is move across, and hopefully you can still see this. Let me check my recording. You can still see this. All right, we're going to... I don't want my... You can look at my history. Admittedly, it's just slides. Look at it. Ooh, lots of slides. Let's just quickly jump in and let's go metallic sea of delocalized electrons. As you can see, I am a terrible typer. All right, images. Let's find a random image in here. This is sort of what we mean. I think I like these images here, like this. Like what we're trying to describe here is that there's all of the metal exists as like a positive sort of, they exist as like a positive ion sort of in a field. And as much as it's a positive ion, we're in like a field. And because we're in a field, we're a solid, and that field allows the electrons that are available to just float throughout. So they just float throughout. So they're just here and they're floating up here, and they come down here and they go down here, and they float around. They do what they want. And then a charge gets applied over here, and the electrons go, ooh, they take that charge and they go, ooh, and they move throughout, and they move it throughout the wire. And that's essentially why we refer to our electrons as having that idea of being like our metals, having that idea of metals as a solid being able to conduct electricity because those electrons are delocalized and there is a sea of them and they can move around. So this is the metallic bonding model. And these electrons are called delocalized as valence electrons break away from the atoms, allowing these electrons to move throughout the lattice. They are held together by a strong electrostatic attraction between the electrons and the ions within the lattice, letter I lattice. So physical properties, they're really malleable, they're really ductile, so they can be pulled apart, they can be smashed. so forth. They can conduct electricity due to already having delocalized electrons. So having that charged particle allows you to conduct electricity, allows the electricity to move throughout, and that's a really important point. They have high boiling points and high melting points, so this is due to the strong electrostatic attraction. So more energy is needed to break these bonds. The metallic bonding model cannot explain the variance between melting and boiling points, the magnetic nature of metals, the various electrical conductivity of metals. So there are some elements of metals which are really different. Some metals are magnetic, some metals are not. Some metals are conductive far more than others. The variance between melting and boiling points is considerable between metals. We don't have a good way of discussing that in terms of this whole metallic bonding ruling. Like, we don't have a good way of doing that. And that's a really important point. There is no good way of discussing that using this whole metallic bonding model that we use. We can discuss that in terms of different models, and it's something that we can talk about. We won't talk about it today. It's something we'll go into detail in class, and it's something that you will be expected to sort of know about. But that's a really good summary for what's going on.